Okay, so I want to show you another real world application of the work that we've done about masses on springs. There's a point of view that says that, well, in the real world, how often do we really see a mass on a spring? Is that a thing anymore? And I'd like to point out that yes, absolutely. In fact, we see masses on springs all the time. In fact, we drive around in them. As specifically, what I'm talking about here is cars. So I want to look at this old exam question here. And let me apologize for the fact that when I imported the or exported the file as a PDF file, it looks like it kind of fuzzied it up a little bit here. So if you have, I think this is legible, but if you'd like to see a crisp image, just go to my exam storage. So 1415 spring, exam 2, question 4. Okay. All right. So older cars, such as your grandfather's in this particular old exam question, had suspension systems that were pretty much a mass on a spring. And let me draw you a picture of what these look like. Here it is, very approximately, of course. The wheel is attached to an axle. The axle is attached indirectly to the frame of the car. Well, it better be, right? That's what's holding up the car. But what it was attached by is a very stiff spring. Very stiff spring, right? That spring is what's holding up the car. And so you can see right away, we have literally a mass on a spring. The car is the mass, and there's the spring. So it's a little bit of a surprising realization, but that's how it works. Also, it's pretty plausible if you think about it. I mean, how else would we design a car? Would we actually have the frame of the car bolted directly to the axle? Well, then it would be a horribly rough ride, right? Every little vibration in the road, you'd be vibrating the whole way down the road. So completely undesirable. Okay. Oh, there we go. Okay, so mass on a spring. Now, there is an extra little design element that is in these old suspension systems. And real quick aside, they don't really do cars like this exactly anymore. However, what they do in cars nowadays is modeled off of this same design. It's still a spring. Maybe they've gotten more clever in terms of how they design the spring. It's still, roughly speaking, this thing that's called a shock absorber that we're going to talk about in a minute. They've gotten maybe more clever in terms of how those works, but roughly speaking, very, very similar even today. But I did make this an old car so that we could keep it simple. Okay, so what is this thing that I'm calling a shock absorber? That is just something that is designed to create friction, basically to dampen oscillations. So if you think about it, if we didn't have any such thing, if we literally just had a mass on a spring, right? The mass on the spring, you hit a bump in the road, the car starts to bounce, and it would just bounce forever, almost forever. Maybe not exactly forever, but cars are heavy. It's a lot of mass. The springs are very, very strong to be able to hold up all that mass, and air friction is very little, right? So, so it would bounce for a long time. Okay. All right, so yeah, this shock absorber just creates a little bit of friction, and it's just like the friction term in our regular mass on a spring examples. So the resistance that it provides is proportional to the speed that the system is moving. And as I've understood it in the past, it's roughly speaking a piston, and as the piston pushes in, that increases the pressure inside of the chamber, and that pressure will leak out through a little hole, but it can only leak out so fast. And so the harder you push it in, the more resistance it gives back as it's trying to leak out to keep up with you pushing it in. And then likewise, when you pull it out, well, now you have negative pressure in the cavity and the air has to come in. So if you pull it out slowly, not much resistance, but if you pull it out, try to pull it out really fast, there's a lot of resistance as that air is trying to keep up with your movement. So not a very complicated design. And again, it's more complicated than that, but that's the rough idea. Okay, so these pieces together, we have the mass on the spring. This term comes from the shock absorber. This is the friction term, right? And then the spring itself is that term. So just like the old mass on a spring examples that we've seen before. Okay, so how much friction should this provide? Right. Well, you want to kind of get that right to some. Well, there's pros and cons, but certainly if the shock absorber is too weak, then there's not enough dampening to actually resist the bouncing, and the car will just bounce on down the road for maybe longer than it really should. Right. This is not good. On the other hand, if the shock absorber is too strong, if it's giving too much resistance, then it's almost like again, that you're just bolted to the axle. And again, you're going to have a rough ride. And that's really, ideally not good. Both of these can lead to bad handling, bad traction with the road. So neither of these is good from a handling standpoint. And again, very complicated and pros and cons and considerations, but anyway. Okay, so a point of view on an ideal for how much shock absorber should there be is to have the critically damped case, such as we discussed in the notes and in the recordings. That is the weakest and therefore gentlest ride that you can possibly have while still eliminating all of the bouncing. It's a nice compromise from a certain point of view. And again, pros and cons and details, and I don't want to, I'm oversimplifying. Okay, so that being the background, let's look at this exam question. And again, you can see a more clear image from looking it up from the PDF file. And this being the differential equation that we're looking at, the current state of your grandfather's old car is that A is equal to 2. So the shock absorbers that he's got in there, the current shock absorbers that he has in there have this amount of resistance. We're ignoring units, obviously. Okay. And this results in an oscillation. So you might say this is too weak, right? He needs a stronger shock absorber to be able to kill that oscillation and thus give his car better handling, but not too strong so as to make his car unnecessarily rough riding and also, again, leading to bad handling. So how, given only this information that A is equal to 2 currently, and information related to that, can he figure out what the right shock absorber is for his car? Now, the additional information that we have is a measurement that you've taken as you're riding in your grandfather's old car, and you have measured with your watch that the frequency of these bounces, right? I mean, he's oscillating, bouncing as he goes down the road. The frequency of those oscillations is this 3/2 pi. Again, sorry for the hard to read background there. Okay. All right. So is this enough information to answer the question? And it turns out that it is. It's kind of wonderful how this works. But with A equal to 2, the differential equation is this, right? There's that A equal to 2. And with A equal to 2, we can just solve for what is the actual frequency of the oscillation. Well, solve for lambda, root of the characteristic polynomial. You get this. We know there's an oscillation. That means that this discriminant clearly has to be negative. Simplifying appropriately, we get that this is the lambda, and thus that this is our omega for that oscillation. And notice it depends on K. And well, of course it does. Of course it depends on K. The stiffer the spring, right? Stiffer springs are going to have a different oscillation. Looser springs are going to have a different oscillation. Okay. So knowing then that the frequency is what it is, knowing that the frequency is 3/2 pi, having solved here that the frequency is this expression, don't forget frequency is omega/2 pi. It's easy to forget that. What we see then is that these two things have to be equal, right? So we can actually solve then for K, solving in that equation for K, and you get K is equal to 10. So, okay, going back up to the original statement of the question, we were told that this is equal to 2. And we were also told the frequency is 3 over 2 pi. This information allows us to determine what that K is. All right, now how does that help us with, our question was to figure out, how do we critically damp the system? Well, if we change shock absorbers, let's see here, we change shock absorbers to a different value, all I have to do is ask, how do I critically damp this system? And the only thing I really needed to know how to critically damp this system is how strong is that spring. And we now know how strong the spring is. We know K. K is, here it is. K is equal to 10. So that being said, with K equal to 10, plug that into there. How do we critically damp this system? Well, we want the discriminant to equal to 0. And then solve for A. And here it is. A needs to be 2 square root of 10, which is a little over 6. So his current shock absorbers of strength 2 are not cutting it, right? This is too weak, and he needs shock absorbers that are significantly stronger at 2 square root of 10, whatever that is, 6 point something. So I think this is a nice old exam question because it's kind of real world realistic. This is certainly a very real world scenario that you have a car, right? We all have cars. We all drive around in cars anyway. Might not own a car, but being able to get the suspension worked out is an obviously important thing. And it's all modeled on this one differential equation. Again, modern cars are a little bit more complicated than this, but this is the main idea. So I think this is a lovely real world application. Okay.